Hi, I'm Peter Banatini, and today we're going to talk about a sequence, how to do T1234. The descriptions of this sequence and the purpose and advantages of this sequence are in the MRM, a recent MRM publication entitled T1234, a distortion-matched structural scan solution to misrepresentation of high-resolution fMRI data. So T1234 is a sequence that uses T1 weighting, 2 inversion pulses, 3D EPI, and 4 combinations of spatial encoding. And it's very effective. It's for matching distortions, and it's specifically tuned for very fast MP2 range, like structural scans for layer fMRI studies. So it's a very useful technique for everyone to use if they want to directly register the data onto high-resolution structural scans.
So first, we need to install a sequence. If you don't have it already, you can grab it from the Siemens App Store of Sequences, the C2P Exchange platform, by typing in this URL. If you're in US or in EU, the URL is slightly different. And then somebody at your institution probably has login credentials already to this App Store where you can download the sequence. If you don't have access to that platform already, you can still do it in the old way by asking your Siemens Collaboration Manager. There are a bunch of sequences that you can choose from. In this C2P Exchange platform, the sequence used in the T1234 is called a VASO sequence. So search for VASO and make sure that you're selecting the one from DZNE. If you look on details, you can see that it's developed by Rüdiger Stirnberg and myself, both authors of this paper. And you can download it for these VE versions over here, specifically the Siemens Terra and 70 Plus scanners. As soon as you have the sequence, then you can set up the protocol, and it's available on GitHub. If you type in GitHub T1234, then you will see a link that sends you to the GitHub repository, and there's a folder T1234, which then shows you PDFs with all the different parameters that you can type into your protocol editor, and then put a person on the table and start your experiments.
Okay, the patient is on the table now and performing a layer fMRI task. And you can see the field of view is over here and the angle is tilted. This angle basically for the most of the layer fMRI doing in this way. In the functional scan, we found the tilt angle at orientation field. And we need to remember the value. Here we have minus 30 degrees. Furthermore, we take note of echo spacing. Here we have 1.12 millisecond and using grapher follow. So the effective echo spacing is 1.12 divided by 4, which comes up 0.28 millisecond. Now we grab the T1234 protocol. Since this is a whole brain protocol, it is most efficient in sagittal orientation. To match the phase encoding direction, we type in the value 30 here. Then, we make sure that the same shim is used. And now we can acquire the data. The scan takes 1 minute 51 seconds with 2 read polarities. Next, we set up the inverse phase series. First, we copy the AP series, we minus 180 degrees from 30 degrees, which is minus 150 degrees. Then click OK. The phase direction now becomes PA. Save the series and change the series description from AP to PA. And we are all set for the scans. The best thing about T1234 is we acquire both scans in less than 4 minutes, which is similar to the time needed for conventional blip up and blip down scans. With T1234, however, we get a full structural scan with them for free. After you acquire all images, you can take them to process offline.
So now that we have all these data, we can start analyzing them. And in case you want to follow along, you can download the very same data and the scripts at this link, layerfMRI.page.link/T1234_tutorial. This brings you to a database folder where you have all the relevant data, as well as the scripts that we're going to use. I have it already downloaded in my folder right over there, and we can quickly look at that. So I have 4 time series here that have magnitude data in there, and I already renamed them according to their inversion time and their phase encoding direction. So here, for example, you see that we have a data set in the AP phase encoding direction that has first inversion time, so we clearly see this gray matter white matter contrast. It has multiple components in there which are referring to the different read direction. So multiple read polarities are included in the same series. Then we have the second inversion direction, which is used as a reference image, which has a longer inversion time and thus less T1 weighting. And then I have the same thing again, but now with a different phase encoding direction, now with a PA direction. And the first thing that we're going to do is do a motion correction of these data. Namely, I'm running AFNI, specifically a 3D alineate, to go through all the runs that have a file with the name TI1 and then align them to each other. And then I'm going to do the same thing with the TI2, the second inversion times. So let's execute that like this. It's going to start and it's called AFNI, and this might take like 2-3 minutes or so. Okay, this seems to be done. So let's look at the results. Now we have additional files in our folder. Namely, we have these MOCO files, which stands for motion correction. So now all of the different time series within the runs and also the different runs are all aligned to each other. So now we can perform the actual T1234 analysis, which is in the second script in that folder, namely the O2_T1_prep scripts. And there, the first step is basically just averaging. I'm averaging the different read polarities which have opposite artifacts to get rid of the fuzzy ripples. And then I'm doing this separately for the AP in the first inversion time and the second inversion time respectively. And then I'm taking the ratio of the first and the second inversion time, which then takes care of any T2 star weighting or receive bias fields, but also proto density that we don't want to have. And this is really following the MP2 range-like reconstruction. So we end up with these uni images, both for the AP and the PA direction. Because this is a division, it means that outside the brain, we are basically dividing 0 by 0, which can result in noise outside the brain, which we then can regularize away, which I'm correcting for in a Laney program that's called ln_mp2 range denoise. Maybe to give you an idea of how this looks like, let's execute this. So first of all, it's executing the averaging of the 2 read polarities, and then very soon we will get to the stage where we have these different ratios already. So they are coming up. So here we have the ratio images, and as you can see, we have this noise outside the brain. And then with the denoising, we're basically regularizing this away, and we have this for the AP and the PA direction. The next thing in the script that is executed is a bias field correction for residual flip angle inhomogeneities. You don't really need that. The bias is not that strong. I found that for later analysis, for example, in FreeSurfer, it still can be advantageous to run this. And this takes a short while. And then comes the combination of the different phase directions, where the AFNI program 3D Warp is using the 2 phase encoding direction as you would do in a blip up down top up like fashion to estimate distortion field in the phase encoding direction only, and then we can use that distortion field to match the same distortion that we have in the functional data. Specifically for that, we need to know the echo spacing, which is why Kenny in the acquisition session highlighted that for our functional protocol we used 1.12 millisecond with Grappa 4, giving us this effective echo spacing. For the T1234, we have a way lower echo spacing effectively because we are using much higher segmentation in there, which helps us also to get a better estimation of the distortion field because we don't have these within slice defacing artifacts anymore. And then at the end, we end up with a distortion field that can transform our T1234 data to the functional space directly, but also we can use those distortion fields to undo any distortions and end up with those distortion-free images. And specifically the blip up-down analysis takes a while and can take up to a few hours. So now, a few hours later that this is all completed, we can look at some output. Just to give you a feel of what this might give you. So for example, here we have then these combined images that are combining the both phase encoding directions, and you can see that they have pretty nice gray matter, white matter contrast, so you directly can pump them through FreeSurfer or FreeSurfer-like analyses that give you these segmentations of gray matter and white matter. And with this, I also want to thank Paul Taylor for help with the scripts that we just went through, and all the co-authors and you for your attention.